Okay guys, hi. This is another video on revolving with the disk method, and I want to give you a little visual. So I'm trying to make this easy for you to kind of see and understand what we're talking about in class. So imagine you have this graph that's in front of you on the screen here, and you shade in an area, the blue region from A to B, and you decide you're going to revolve that area around the x-axis. You're actually going to spin it around the x-axis. That's going to look like this. It's going to spin all the way around, and it's going to form a solid. And what I want to do is I want to study this solid a little bit. I want to figure out what's the volume of it. If I was to take this object and fill it up with water, how much water would it take to fill it up, basically? So my whole goal, and I'm going to write on here, is I want to take this thing and I want to figure out what is its volume. And that is kind of the focus of this whole chapter, is finding volume of objects. So to figure this out, we have some calculus strategies we could use. And one of the strategies looks like this. We're going to chop this region up. I'm going to show you a different screen here. We're going to take this graph and basically shade it in and cut a little rectangle out of it, a little slice. And imagine just spinning that one rectangle around the x-axis here. Take a look. You can see it on the screen there spinning. Check out what happens when you take a single rectangle. Remember when we found area under curves, how we did LRAM and RRAM, and we cut it up into little rectangles to find the area? Now I'm taking those little rectangles, but I'm rotating them. And so this is what happens. I'm going to write on the screen again here. We get this disk, this shape. So we get a disk. I'm going to write it over here. And basically the disk looks like a little coin. And it's formed by one rectangle spinning all the way around. So there's some important properties of this disk. For one, it has a radius, which I'm going to mark right there. Now if you look at the graph, the radius goes from here to here. That's the radius of the disk. Another thing about the disk is down at the bottom, it has a thickness. It depends on how skinny that rectangle is to figure out how thick it's going to be when it spins around. So this is its thickness, which I'm going to denote as W for width. And if I needed to find the volume of this one single disk, what I would do is use this formula, the volume of the disk. Okay, I'm going to write it over here, volume for the disk. The volume of the disk is when you basically take the area of it, which is just a circle, and times it by the thickness. So volume equals area times thickness. Well, area of a circle is pi r squared. And thickness, remember I called it W, so I'm going to write times the thickness, which is W. Now, the plan with this is that's just the volume of a single disk. What I'm really going to do is I'm going to chop up this space into thousands and thousands of little tiny disks and add up the volume of every single one of them to get the whole entire object. That's my plan. So let's look at what that would look like. We need a picture, a visual. So I'm going to switch screens here. Check this out. Here's that one disk. I'm going to show the area. Remember, this is what we spun around the x-axis. When I revolved that one disk, it looked like this. And we talked about the thickness and the radius. Well, now I'm going to fill up that space with a lot of rectangles. So here's a bunch of rectangles. Picture spinning every single one of those rectangles around, and you're going to see all these different disks. And eventually, if you spin all the rectangles around, those disks kind of compiled together to make our object. You can see the 3D shape here on the screen. You can see that that's basically this thing, just not as smooth looking. Now, if you look at each rectangle, these are pretty wide rectangles. If I made them infinitely skinny, then I could get a really good calculation for the volume of this thing. So that's kind of what the disk method is all about. Our strategy, it's right on here, is we're going to sum up all these rectangles. So in calculus, when you want to add up a bunch of things, that's the integral. Remember, the integral is the summation symbol. It's a long elongated S basically. So we're going to add up every single disk, and we're going to add it up from A to B on this graph. And basically what I'm going to do is I'm going to take pi r squared times the thickness. Pi r squared times, remember we call the thickness the width. I'm going to write this though here in a second. I don't really like writing pi r squared times the width, because how wide are each rectangle going to be? Well, it depends on how many rectangles you fit in there. I want to fit infinitely many rectangles. So let's erase this. Let's not write W for width. I don't like that plan. Let's say the width is so skinny we can't even measure it. It's a width of delta x, or I'm going to call it dx. Okay? The radius, I'm also going to erase this radius squared here. And the pi, I'm going to erase that too. The pi is just a number. So let's put the pi out in front. And then the radius squared, I'm going to rewrite that also. Remember, the radius goes from here to here on the disk. If you can see that. So if you think about what's determining the radius to go from here to here, or like if I picked a rectangle out here from here to here, that's the radius. Well, I would say this is determining the radius. This is the radius, the function. So I'm going to write radical x squared. And then this is going to represent the volume of my object. Basically what this formula says is add up every single disk from A to B with pi r squared times the thickness. And if you can solve this integral, you can basically get your answer for volume. So this is kind of just a visual aid to kind of help you guys to kind of picture what's going on. Hopefully it helps. There's a couple other videos that'll be coming out, so I guess stay tuned.